Hi, my name is E.J. Daigle. I'm the Director of Robotics and Manufacturing here at Dunwoody College Technology. And today we're going to talk about relay logic circuits. Some topic learning objectives that I'd like to cover today. First one is, upon the successful completion of this topic, trainees should be able to describe the physical construction and operation of a relay. The trainee should be able to describe how to use relays to control electronic devices. And the trainee should be able to wire a simple relay control circuit. So the first thing I want to talk about is there are several different types of relays out there that you may see. I've got a few samples of them here. Some of them are much larger and they are what we call contactors. They can be used to start motors. They can be used to control large current devices. A couple examples of those right here. And then there's a lot of relays that are more of an ice cube type relay, like this relay here. And these are generally used in more of a control logic circuit. And then there's solid state relays and transistor based relays and a lot of other relays too, but I just wanted to show at least a couple of samples there. Now if we go over here, this is the physical construction of a relay, to kind of give you an example here. I'll try to grab a different marker here, give you a different color. There are a set of terminals just for the coil. So you see a couple of screw terminals here that you'll be able to pull wires up to when we get up into the lab. If I pull wires to here, I've got to have a return path on the other wire. In some cases, this coil inside of here is a DC coil, and it's important that I use direct current with these terminals. In other cases, this might be an AC coil, in which case it would be fine for me to use alternating current with this particular relay. Let's say for practical purposes this is a DC relay. I would wire from a DC source, something like this, maybe it's 24 volts DC, and I would wire perhaps through a switch and maybe over to this contact. Now that would supply current through the coil and give me a path through that coil. But then I'd also need a return path. So from the other side, I would run over to here and I'd have a complete path. When I close this switch, I would get current through the coil and back to the power source. Now all the coil does is the coil is a big electromagnet, and its sole purpose in life is to move this armature up here. This is an armature here. Right here. The idea is that this would be a magnet here, an electromagnet that would energize, and it would pull this armature down. And whenever there wasn't current through this coil, the armature would spring back up because of the spring that we see over here. So we can see that this spring is actually attached to the armature itself, and the armature pivots on this pivot point right here. And what happens is when I energize the coil, the armature is pulled down by the magnet, and when I release power to the coil, the spring is going to pull back down on the armature and bring it back up. So basically this armature is going to bounce between 2 points. And this would be 1 point here and this would be 1 point here. These are what we call our normally open and normally closed contacts. So as I look at this drawing here, what I can see is right now my coil is de-energized. So the switch is off, the coil is de-energized, the spring is pulling on this, there's no magnetism to pull on the armature, and what happens is this armature flies up to the normally closed contact. And what normally closed means, this NC stands for normally closed, it means that it's normally closed without power on the coil. So in this particular example, the armature is sitting on the normally closed contact. As soon as I energize this, if I was to close this switch, now I have current flow. So the switch is closed, and I'm going to get current flow up and through my coil and back to the source. As soon as there is current flow, this becomes an electromagnet. At that point, the armature is pulled down, and now I'm going to go down to the normally open contact. So we'll use blue to represent that. But the armature would change states, and it would now be sitting down here. And it would be pulling on the spring a little bit. So the second that I release this energy or open this switch, the magnet goes away and the spring pulls back on it and takes it back up. So that's what normally open and normally closed contacts mean. Normally closed meaning closed when power is on, and normally open meaning it's open when power is on. There's also a common terminal up here. The common terminal is a point where I can wire to deliver power through a contact to a control device. So this is the basic relay construction. Let's move over to a control circuit and look at how this works in real life. A lot of times when we're working with control circuits, we'll work with push buttons. You'll actually see an example of a push button right here. This is a push button station. There's a start push button on this station, and there's a stop push button on this station. And in our example, I'll talk a little bit about start and stop and how they're going to be used in this control circuit. So we'll go back up to the control circuit. This is a schematic diagram. We like to call this a ladder diagram because it's got a power rail, and then it's got rungs like a ladder would have. And if I wanted to add another circuit, I would just extend the lines and add another rung. In this case, you'll see that the stop push button, much like a normally closed contact, it's shown in its closed state. All stop push buttons are going to be normally closed, meaning they can deliver power without someone pressing them. All start push buttons are going to be normally open, meaning they will only deliver power when they are pressed. So we show that it's not making contact. When I press it, it's going to go down and make contact. And then I have my coil here. This is the schematic representation of a relay coil. So I can see my coil here is wired up in series with the stop, in series with the start, and back to the power rail, making a complete circuit. Also, though, I have the normally open contacts. I've got two. K1, this is the reference designator of my relay. A lot of times we'll use K to reference a relay, K1, K2, K3, whatever it might be. In this case, the contacts still keep that reference designator, K1. But I'm going to put a -NO or a -NO, or in some cases a -NC to represent that it's a normally open or a normally closed contact. I could also see a normally closed contact if I was to see something like this in a drawing, because it'd be shown drawn in its de-energized state, and normally closed would appear to be closed. Okay? Now let's talk about the way this works. Right now, the way this circuit's going to work is there is power or current being delivered right to this point, because the stop push button is closed. It's normally closed. So there's power sitting on the start push button waiting to energize something. In this case, the second I hit the start push button, I press it down, it's going to make contact. When it makes contact, it's going to deliver power over to the coil. The coil is going to consume that energy. It's going to become magnetized again, and all of its contacts are going to switch positions. So the normally open contacts are going to close, just like we saw in our diagram a minute ago. And any normally closed contacts would open, which means they are also delivering power now, like so. There, and there. And now I have a buzzer down here that's going to sound. So that's going to work great. Now if I release the start push button, if I release this button, what's going to happen is this line is going to go away, but the buzzer is going to stay on. And the reason why the buzzer is going to stay on is because we have a holding contact. So right here we have a holding circuit. Those contacts are not going to change state until they lose power. Well, they have not lost power because no one hit the stop push button, so they haven't lost power, so they're holding this control relay on. So both of the contacts are going to remain closed. And now if I want to shut this circuit off, the only way to shut this circuit off is to press the stop push button, which is a normally closed push button. It'll look like this now. That's going to release all of the current. We're not going to have any current. We're going to remove current from our circuit. There's no way for electrons to flow through here. So now the holding circuit's going to go away. This circuit down here is going to go away. And all of these normally open contacts are going to go back to their normally open positions. Just like so. So hopefully that gives you a good idea. Now if I release that stop push button at this point, it goes back to normally closed, but I don't have any current paths, and we're in our normally open, de-energized state. So what I'd like to do now is at this point we'll go up into the lab and we'll take a look at how we'd wire this circuit up and how we'd make this circuit work in real life.